All right, good afternoon, or morning, I guess. Sorry I couldn't be here today, but I'm going to go over the 6-year-old design and performance specifications and the injury assessment reference values. And these are basically what we're going to have to be designing around for the rest of the semester. So let me go over what the difference is between design specs and performance specs again briefly. In the design specs, these are basically limitations on dimensions, masses, materials, mates, those sorts of things. They're of course going to directly impact the design process. They're not flexible. And we're going to formulate those today in this lecture. We'll all design around a common set of design specs. Now the performance specifications are requirements for function. And they can usually be met by a wide variety of designs. So we're going to have a lot of individual flexibility as teams in how we meet the performance specs. You're going to formulate these and present them in lab on October 11th. So you need to start thinking about them ASAP. All right, so in the design specs, we're basically going to design our neck to mate with the current Hybrid 3 6-year-old head and torso. So we want it to look as it does in the figure here. To get a laser pointer to show up, but I don't know if it's going to happen or not. So we don't want to change the configuration, the relative configuration of the torso and the head. We're just going to stick our neck in there. So we've got a constraint on the length. We've got a constraint on the weight. We've got a constraint on the attitude of the neck. By that I mean the angle. And we have hole patterns in the torso and in the head already. And our neck must mate with those hole patterns. So let's look at the length specification first. We're going to pull this out of the Hybrid 3 engineering drawings that are available on Sakai. The head and neck are connected by a load cell. The load cell is mounted rigidly to the head. And on the left-hand side, you can see the load cell. Hopefully my laser pointer is showing. I don't know if it's not. Oh well. The rubber neck on the right basically is attached to the load cell with a pin joint, which is highlighted by the circle number 10 call out here. And we're going to replace all that, the load cell and the neck, with our own design. And we have to get the overall length right, though. So you can see the OC pin attaches the neck to the load cell, which is rigidly attached to the head. And as I said, there's the force transducer there. Okay, I should have animated that first, I guess. All right, so hopefully that's all clear. Now, in terms of dimensions, if we look at the drawings, we can see that the overall neck length of the at least the butyl rubber part and the two end caps is 3¼ inches. So that's our main element. On top of that, we've got this pin. It's a cap for the top of the neck. And if we go down and look at the dimensions on that, you can see it's 0.287 inches up to one reference line, which is the top surface, and then another 0.375 inches to the middle of the OC pin. So if we sum all that up, we come up with 3.912 inches, and converting that to metric, overall we've got 99.4 millimeters so far. Now we need the distance between the center of the OC pin to the base of the Hybrid 3 head. So we'll get that from these drawings. You can see it on the upper right here. The distance from the center of the OC pin to the base of the cast aluminum head is 0.38 inches. So we're going to add that in. That's another 9.7 millimeters. So our overall total neck length ends up being 109 millimeters. So here's our first design spec. Our necks must be 109 millimeters from base to top. Now, how do we mate them? Well, the base of the skull has 4 holes in it in a circumferential pattern, and they're called out here. So you just need to look at the engineering drawings for the base of the skull. And we're going to have 4 quarter-inch holes essentially on looks like a 3-inch diameter, equally spaced. So that's the whole pattern. So you have to have a mating plate on the top of your head that will exactly match up with this hole pattern. And then on the bottom, you've already modeled the bottom bracket in SolidWorks. So what you're going to do here is take that same hole pattern that's on the SolidWorks bottom bracket, and the bottom of your neck must have another plate that is going to match up with those holes. And I think those are all 1032s and on a 1-inch radius, so quite different than the one at the top of the head. So that's the mates. So we've got a mating hole pattern for the top and bottom. We've got an overall length. As I said, the attitude can't change. That means the basic alignment of the hole pattern in the top of the neck and the bottom of the neck must be the same as it is in the current Hybrid 3 dummy. In terms of weight, there is no current specification for the Hybrid 3 6-year-old. I can tell you that the adult Hybrid 3 neck weighs 1.7 kilograms. And I'm going to put it to you. What should we do? Should we have a design spec for the neck? I think we should. And one of your tasks is going to be to determine what that should be. Just the cervical spine, the whole neck. What do you think that design spec should be? So that's something you're going to present on the 11th. All right, so that's it for the design specs. The next thing we're going to get into is the performance specifications. We're going to break these down into two types, kinetic, and we're going to need these for accurate injury assessment and in terms of what the loads are in the neck, and then kinematic. We're going to need those to be sure the head is in the right place at the right time if you're testing a seat system. So for the kinetic performance specs, we need some specs for tension and compression. We're going to throw out bending this year because bending as an injury criteria is not something we really get into very much. You cannot break the neck very easily in bending, so we're just going to focus on tension and compression. And then for kinematics, we've got a whole set of specifications that we're actually going to give you, and Courtney's going to present those today after you're done watching this. All right, the literature on which we're basing all of these specs is listed here. This is required reading for everybody. There's about 10 or 11 articles here, and they're all important in terms of characterizing the biomechanics of the neck, the pediatric neck, and also in telling us, particularly Irwin and Mertz, on how we scale from one size to another and how we might scale from adults to kids. Because, as you recall, we have a lot of info on adults and not so much on the kids. So this is all available on Sakai, and you need to read it as you formulate your specifications. So let's take, for example, pediatric tension specification. So we're going to need a stiffness, and that stiffness has got to come from the data that we have. So what I've put up here is data from Luck 2011. And what I want you to focus on is the black line, the power law model, for the stiffness from 50 to 100% of failure. So we're looking at stiffness as a function of age, and you can see it increases. And the power law model is circled here in red. All you need to do is throw in an age in months, and you should get an estimate for stiffness and tension. So that should give us tension for the cervical spine, at least for the upper cervical spine, OC2. Now keep in mind this is just the OC2 segment. So we've got to translate that into a whole spine criteria because we're building whole spines. So what might we do that? Well, let's actually go and look at the adult data from DIB in 2009. And he tabulated failure force and failure displacement. And everything you need is really circled here. So comparing apples to apples, let's look at the OC2 force at failure for the adult. And that way we can compare it to the child. 1,468 with a standard deviation of 480. So quite a spread. And then let's look at the displacement. We've got a mean of 4.2 and standard deviation of 0.8, and that's in millimeters. So dividing the two, we can get a stiffness for the upper cervical spine for the adult. Now what we have for the adult that we don't have for the 6-year-old is actually whole spine stiffness as well. Nowhere do we have any data for pediatric whole spine stiffness, although it might be useful to check O-Yang to see if the results you get ultimately are anywhere in the ballpark. So for the whole spine, if you look at Dib et al. Again, 2009, we can calculate a stiffness of about 90 newtons per millimeter in this particular test where we loaded over the occipital condyle. So that's the closest to pure tension that we have. So adult whole spines are somewhere around 90 newtons per millimeter. The adult OC2, which we can get from the same paper, is about 324 newtons per millimeter. It's a shorter segment and overall stiffer. So maybe we can make use of this ratio to estimate what whole spine is relative to OC2, and maybe that ratio will hold for kids, which might allow us to do something with the pediatric OC2 data. So those are sorts of the sorts of analyses that you need to do. When you're doing tension, though, you got to be a little careful, or you have to be very careful, in fact. The muscles play an important role. The effect of the muscles can be found in Chansey et al., 2003. So you need to have a look at that paper and see basically how much you have to correct for if you have a stiffness criteria for the ligamentous part of the neck. How much do the muscles contribute? How much stiffer does it get? I recommend you look at Chansey 2003. All right, so what you're going to present as teams are corridors. Now, these corridors are completely random, but this is what I want you to present to the class, and I want you to make a case that your corridor is the one we should be using. So we have a compressive stiffness here. This is displacement versus force in red, so negative is compression. The line down the middle is the mean, and you have uncertainty here. You have uncertainty in your force values. You have uncertainty in your displacement values. You can use that uncertainty to come up with a confidence interval, or at least a one standard deviation corridor for what your compressive stiffness should be. Same thing for tension. You might elect to have them the same. You might not. It should all be based on something rational that you can point to in the literature. So this plot right here is one of the things that you need to present to the class on the 11th. Now, as I said, on the kinematic side, we're going to give you the corridors that you need. Last year we formulated them as a class, but since then we've actually published a few that we think are appropriate for the 6-year-old. I just want to give you a little bit of background on where these came from, and then Courtney's going to talk to you a little bit about specifically what we've done. So back in this was in the 70s, I think. A whole bunch of volunteer tests were done on Navy seamen, where they were subjected to frontal accelerations, and all their head kinematics were carefully recorded, as well as their head the kinematics of their torsos. So I think this paper is available also, but long story short, coming out of this series of studies and then a number of analyses that were done on that data since, there are two sort of kinematic corridors that are in common use in the automotive industry and in dummy design. These are called the NBDL corridors, Naval Biodynamics Lab. And the top one up here is the head center of gravity trajectory relative to T1. So basically the head starts out at the top of the corridor, upper left, goes down towards the lower right, and that's basically how the head sort of flips forward during a frontal deceleration. And ideally, an adult dummy's head would fit right inside of that corridor during the loading phase. The other important thing, and the thing that is sort of key to getting the kinematics of dummies right, is the angle corridor. This one's a little hard to explain, but basically the angle between the head and the neck doesn't change much initially. So you can see this, we're looking at the lower right plot. You go down to 0, 0, that's where we're starting. So initially during the event, there's not much change in the angle between the head and the and I guess ground. Not much relative change. And then all of a sudden we have a lot of change in that angle. So this initial from 0, at least vertically, to 30 is what we call head lag. That means the head is basically staying level there. And it might take you a little while to kind of process what all this means, but it means that the head is staying level for the initial part of the impact, and then it snaps down. So that head staying level basically means the chin is projecting out, and that is a characteristic that we want to be able to capture in our dummies. It's very human, and it's something that the dummies don't do very well at all. All right, so we have Excel versions of the adult corridors, and I guess this is all legacy from last year. So don't worry about this. I'll just fly through this because we're actually going to give these corridors. So that's one set of specifications. And then we also have another set of specifications that come to us from the Children's Hospital of Philadelphia, where they ran, as I mentioned last time, some low-speed bumper car style accelerations on a number of kids and on adults as well. So I won't get into the kinematics here too much, other than to show you what sort of typical head excursion data looks like. But ultimately, what we have is a corridor that we can design for the z displacement of the ear as a function of time. That's what's on the top, and the x displacement of the ear as a function of time. That's on the bottom. So these are very low velocity impacts, but it would be, and we're really going to be designing around the higher ones, but it would be really nice to check and see how well we do against this data set. So this is really more of a secondary validation than a primary, because these were generated at exposures that are way below injurious thresholds. So we don't want to design around those. We want to design around the NBDL, which are much higher exposures. But if we can come back and fit these, then we'll feel pretty proud of ourselves, I think. All right, the EAM is the external auditory meatus. It's easy to see. It's basically the hole in your ear. All right, then the last thing I want to talk about is certification tests. When you sell a dummy, the end user has to be able to do a fairly simple test to make sure that the dummy is still in spec. So what I'm showing you here is a certification test for the 50th percentile male, and it's basically a head rotation versus time. So let me walk you through this slowly. The blue box is basically where the peak flexion head rotation should occur. So from time 0, we start at a 0 degree head rotation. Our head rotation should peak there within the blue box. So somewhere between, well, it's looking like 60 and 70 milliseconds. And it should peak at somewhere between ballpark 60 and 70 degrees of rotation. So that's where the peak should be. And then it should return back to 0, meaning the head should come back to a 0 degrees of rotation somewhere in this red line. So that's what the return line means. So we peak, and then we come back to 0 somewhere in there. It doesn't matter how we get there. We just want to peak at about the right time and return at about the right time. That will force us to meet some amount of bending stiffness criteria. So we need to be in the ballpark with bending. And then the extension is just the opposite. We peak a little later and with a little bit more latitude in terms of when we peak. That box is bigger, and we return later as well. So this tells us that our flexion response should be a little stiffer than our extension response because it peaks earlier and returns earlier. All right, I hope that was clear. If not, we'll talk about it some more. But suffice it to say, what I'm giving you is the hybrid 350th male certification. We need to turn this into a pediatric certification test. So your job is to take these boxes, and I'll make the Excel file available to you, and shift them wherever you want to shift them so that you think they're the best certification test for a 6th or a 6-year-old pediatric test dummy. And then the last thing is injury assessment reference values. We need a number that we can hang our hat on to say, okay, we're going to get a tension injury if we exceed this value, or we're going to get a compression injury if we exceed this other value. I recommend you look at the tension data from DIB in 2009, Luck 2012, and Nuckley 2013. I think that'll give you all the information you need to come up with a tension criteria. And remember to consider the effect of muscles from Chansey 2003 when you formulate this. And then for compression, we don't have as much data. You're going to have to do the best you can, but see what you can come up with looking at the papers listed here. We have a lot on adults. We've got a little bit on kids from Nuckley et al. And maybe we can learn something about the ratios or do something clever statistically to come up with a compression criteria. Okay, so your deliverables to the class on October 11th are a 15-minute PowerPoint presentation, and we'll have 15 minutes of discussion, so 20 minutes overall for each team. We'll make those PowerPoints available on Sakai so that we can process them after all the talks are done. Because the next time we meet after we're presenting, we're going to cast votes on a final consensus for the performance specifications, not the design. Those are fixed. We're just going to vote on the performance specs. So each team is going to give the class a spec and a justification for weight, a spec and a justification for tension stiffness and compression stiffness. You're going to give us a spec for injury reference values in tension and in compression. And then you're also going to give us a spec for the certification test. You're going to present that Excel plot and what you think would be appropriate for a 6-year-old. As I said, the kinematics we're going to give you the kinematic specs. But these you have to do as teams and present to the class, and then we'll reach a consensus together on what common set of performance specs we're going to design around. Okay, on top of that, I want you to start thinking about what your preliminary design concepts are. You have the anatomy of the neck. You've got a basic ballpark idea of where we're going in terms of stiffnesses, and you've got firm design specs. So I want you to be able to present on the 4th just an 8-minute presentation of what your initial design concepts are. And I don't want anything formal here. This is quick and dirty. Show us what your designs are. Show us what your out-of-the-box thinking is. I want sketches, and the only specifics I really want is, what equations are you going to use to kind of get your design in the ballpark, at least in terms of tension and compression. I want you to be able to discuss what aspects of the design address which performance spec. Like, do you have a specific element that addresses tension, and are you somehow decoupling tension from compression? Is there anything you're going to do to try to get head lag in the model? That kind of thing. And then you also might want to discuss what could you tune in your model if you're off. So if you're too stiff in tension, what are you going to change? If you're not hitting the certification spec on time, or you're getting too quick of a peak head displacement, what do you think you can change? So those are the only real specifics we want. But this is basically to get you thinking about what these designs are going to look like, get you some quick feedback from the class and from Brian and I, and that way you're going to hopefully hit the ground running when it comes down to starting some SolidWorks models. Okay, in the meantime, also think about what Brian and I can give you in terms of literature, FE training, any other information that you need. We are now in the design process, full bore. We're available when you need us, certainly during class and lab, and also by email. And we'll set up a Piazza page as well, so we can communicate that way. But you need to ask questions, and you need to ask them as soon as you have them.